Hello everyone, this is Lab 4, and this will be going over oscillation. So, this is the introduction, and the purpose of this lab is to take an object moving in the back and forth motion and compare its data to a model based on the numbers from the experiment. And we'll be using a mass hanging from a spring and let it go and observe its movements. So, basically, what we're going to do is we're going to create a video where we're going to have an object hanging on a spring, and then we're going to take that data and we're going to import it into a file using Python. And the data that we get from the Python file will compare to the data collected from the experiment. So for our system and surroundings, we have the mass, the spring, and the earth as our system, and as our surroundings, we have nothing. And when doing the calculations for this lab, we'll be using the energy principle, which in this case is delta E equals delta K plus delta UG plus delta US equal to 0. And delta E is a change in energy, delta K is a change in kinetic energy, delta UG is a change in gravitational potential energy, and delta US is a change in the spring potential energy. And the reason it's set to 0 is because we have nothing in our surroundings, which means there's zero work being done by the surroundings. And for our variables, K is equal to 1 half mv squared, UG is equal to mgy, and US is equal to 1 half ks squared. Now, this is our experiment. As you can see, we have the video that I discussed earlier on an earlier slide. And once we collect data from when we drop the object and let it move around on the spring, it plotted every point on the graph, and to the right we can see those points, and it's moving in an oscillating pattern, which is expected. And we have the numbers in the bottom right corner. Now, before we get into the code, we want to figure out how to find some variables, which is T, the period of oscillation, K, the stiffness, and L naught, which is the length of the spring when it's relaxed. So the way I found T is I took the average after 3 oscillations, which turned out to be 1.551. And the way I found K is I did algebra from T and I isolated it to K, and that's the formula I got for that. And for L naught, I did algebra setting the force of gravity equal to the spring force, and then I got L naught is equal to L minus mg over K. Now, the variables and formulas that we're using in the lab is presented here. So we have the mass of the ball, 0.402, and the initial position from the experiment is negative 0.082, negative 0.661, and 0. T, we're starting at 0, and our delta T is 1 over 2/10 because we want small intervals. And G is 9.8, the spring constant is 6.59, and the L naught is 0.1. And we use the position update formula for ball dot position. We have L as ball dot position minus spring dot position, L hat, which is L over the magnitude of L, and we have S, which is the magnitude of L minus L naught. Then we have our K, UG, US, and E. E being 0 since we have nothing in our surroundings, and K as 1 half ball dot M magnitude ball dot velocity squared. UG is mass of the ball times G times the position of the ball in the Y direction, and US 1 half times KS times S squared. And those are all the variables and formulas that we have. So once we finish the experiment in the code, we get a graph with The blue line representing delta K, red being delta U graph, and green being delta U spring, and orange being delta E, as you can see. And the graphs borderline are the same. They move in the same patterns with the model versus the experiment. So what does this mean? Is the energy principle satisfied? Yes, because when all the changes in energy of the plots are added up, they all add up to zero, which is how the formula is set up because there's no surroundings. And that concludes this lab.